So we're going to talk about the fundamental theorem of calculus, the derivative of the integral form. So let's just recall what this says. To start with, we covered this in the flip class video. So let's let y, say, be some function f of t, and let's suppose this is continuous on some interval ab. Let's set capital F of x to be the integral from a to x of f of t dt. Then f of x is continuous on AB, it's differentiable on AB, and no, closed interval and then open interval, and then we actually have that the derivative of this is the function. So the way I said we could think about this is that you're taking the derivative of the integral, and that essentially undoes the integral. So you could also write this, if we wanted to, with this notation. Okay, so what we're going to do now is just see some examples of this. We already saw one simple example in the flip class video, so let's try some other ones. So for all of these, we're just going to find f prime of x, and we'll just use different functions here. So let's start with f of x being integral, say, from 2 to x of sine of t over t dt. So for this one, it's fairly straightforward. We just apply the theorem. So our little f is just sine of t over t. So the fundamental theorem says this is just sine x over x. So fairly straightforward. So let's try one that's not quite. We're going to gradually build up in difficulty here. So for this one, let's go from x to 1 of sine squared of t dt. Now, when we had our fundamental theorem, if we look back above it, what it says, we start at the edge of an interval a and we go to the value x and take the derivative of that. Well, this isn't in that form because it starts at x and goes to a number. So what we need to do is use one of our properties of our integral that says that we can switch the order on the limit of integration as long as we put a negative out front. So now this is in the correct form. So f prime of x then is going to be negative, and now I just get sine squared x. So we had to do a step there first. Let's try another one. So let's say f of x is integral from 2 to x squared of, let's say, arctangent of t dt. So this is also not exactly like what we have for the fundamental theorem, because notice I have x squared here instead. So I can think of this as like a chain rule. So I can think of this g of x as x squared now. So now when I take the derivative using the fundamental theorem, I'm going to have arctangent, and then I have to put the x squared in, and then I need the derivative of x squared from chain rule, because it's in the function inside the function. So this becomes 2x arctangent of x squared. Okay, let's try one more, basically going through all the possible cases of how this could be complicated. Now we don't always have to use t inside, so maybe let's just put something different just to make sure we've seen it without a t. It just has to be some variable other than x. So we'll use z's this time. So again, we don't have the situation where it's going from a number to a function or to x, But we can use properties of integrals. So remember, I can break my integral up like this. So that was one of our properties of integrals. And now I'll use the same trick on the first one and switch the order of the limits. And the second one is fine. I'll just have to use chain rule on it, but at least it's from a constant to a function of x. So we haven't taken any derivatives yet. We've just rewritten our function f. But now we can take the derivative, and we're just going to use the fundamental theorem of calculus on each one. So for this first one, I'm going to get the negative stays out there, and then I just, since it's just 2x, I just replace the z's with x's. And for the second one, I'm going to put in my function. Then I need to multiply by the derivative of that function for chain rule. So this becomes minus x squared over x to the fourth plus 1. Plus, and then I get an x here. On the bottom, I'm going to get x squared plus 1. And then this is multiplied by 1/2 x to the minus 1/2. So if you want to simplify this a little bit more, and that's our derivative. Okay, let's see one more application of how we can use this. So let's let my function here be the integral, say, from 2 to x of 1 over natural log of t dt. And this is for x bigger than or equal to 2. So now let's note here, if we take the derivative, f prime of x here is just 1 over natural log of x, which we could also write as natural log of x to the negative 1. And so now, as long as, if we remember what natural log of x looks like, it's 0 when x is equal to 1, and otherwise it's positive. So we have f prime of x is positive for x bigger than or equal to 2. So f of x is an increasing function. And we can also take the second derivative of this, and this becomes minus 1 natural log of x to the minus 2 times 1 over x. So this is minus 1 over x natural log of x squared. And so now this is negative for all x bigger than or equal to 2. So that tells us f is concave down. And then one more thing we get is if we look at the f of 2, well, this is the integral from 2 to 2 of 1 over natural log of t dt. Well, if we're thinking of this geometrically, we can see that this is just the interval of length 0, so this has no area, so this is 0. So I can now sketch a graph of what my f of x looks like. So I know that at x equals 2, I'm at 0, and then I'm increasing and concave down. So it's going to look something like this.